Hi everyone. Today let's look at a classic problem. Zigzag conversion. Opening. We are given a string and a number of rows. We write the string in a zigzag pattern across those rows. First straight down, then diagonally up to the top, then straight down again, repeating until every character is placed. After laying out all the characters, we read the pattern row by row, top to bottom, and concatenate those rows into the answer. As an example, with 3 rows, the string spelled P-A-Y-P-A-L-I-S-H-I-R-I-N. G becomes the result spelled P-A-H-N-A-P-L-S-I-I-G-Y-I-R. Naive approach. A straightforward solution is to actually simulate the zigzag. We create 1 bucket per row, then walk through the string character by character, moving a pointer down the rows until it hits the bottom, then back up until it hits the top, and so on, dropping each character into the current row's bucket. At the end, we join all the buckets from top to bottom. This works and is easy to follow, but it stores every row and walks the string with a changing direction. We can avoid the simulation entirely by computing each character's position with a simple formula. Core idea. The key insight is that the zigzag repeats in a fixed cycle. In every cycle, the pen travels down through all the rows, then climbs back up along the diagonal, skipping the very top and bottom on the way up. 1 full cycle, therefore, covers 2 times the number of rows minus 2 characters. Once we know this cycle length, every character in a given row sits at a predictable offset from the start of its cycle. So instead of building a grid, we go row by row, and within each row, we jump cycle by cycle, pulling out exactly the characters that belong to that row. The top and bottom rows get 1 character per cycle, and every middle row gets 2, 1 on the way down and 1 on the diagonal. Key details. A few details keep the formula correct. First, if the number of rows is 1 or is at least as large as the string length, there is no zigzag at all. So we hand back the original string unchanged. Second, the cycle length is 2 times the number of rows, minus 2. Third, the character on the downward stroke sits at the position given by the cycle number times the cycle length plus the current row. Fourth, only the middle rows, neither the top nor the bottom, have a second character on the diagonal, and its position is the downward position plus the cycle length, minus 2 times the current row. Fifth, before taking any character, we check that its position is still within the string. When the downward position is out of range, we stop that row entirely. When only the diagonal position is out of range, we skip that 1 character and move on. Walkthrough. Let's trace the first example. We are given the string spelled P-A-Y-P-A-L-I-S-H-I-R-I-N-G, 14 characters long, and we want to lay it out across 3 rows, then read it row by row. We enter the convert function. The length of the string is 14, so we will place these 14 characters into a zigzag of 3 rows and then read them back. First, we check the guard. The number of rows is 3, which is not 1, and 3 is less than 14. So there is a real zigzag to compute, and we continue. Now we compute the cycle length. 2 times the number of rows. 3 minus 2 gives 6 minus 2, which is 4. So 1 full zigzag cycle spans 4 characters. We begin the outer loop on the top row, row 0. The top row only receives characters on the downward stroke, 1 per cycle, so it is the simplest row to collect. In the first cycle of row 0, the downward position is the cycle number, 0, times the cycle length, 4, plus the current row, 0, which gives 0. Position 0 holds the letter P, so we append P to the result. Moving to the next cycle, the downward position is 1 times 4 plus 0, which is 4. Position 4 holds the letter A, so we append A. The result so far is P, then A. In the next cycle, the downward position is 2 times 4 plus 0, which is 8. Position 8 holds the letter H, so we append H. The result so far is PAH. In the next cycle, the downward position is 3 times 4 plus 0, which is 12. Position 12 holds the letter N, so we append N. The top row is now complete with the letters PAHN. In the next cycle, the downward position would be 4 times 4 plus 0, which is 16. Since 16 is past the end of the 14-character string, we stop the inner loop and finish row 0. Now we move to the middle row, row 1. This is where it gets interesting, because middle rows collect 2 characters per cycle, 1 on the downward stroke and 1 on the diagonal. In the first cycle of row 1, the downward position is 0 times 4 plus 1, which is 1. Position 1 holds the letter A, so we append A. Since row 1 is a middle row, we also look at the diagonal. The diagonal position is the downward position, 1 plus an offset. The offset is the cycle length, 4 minus 2 times the current row, 1, which is 4 minus 2, giving 2. So the diagonal position is 1 plus 2, which is 3. Position 3 holds the letter P, so we append P as well. In the next cycle, the downward position is 1 times 4 plus 1, which is 5. Position 5 holds the letter L, so we append L. The diagonal position is 5 plus the same offset of 2, which is 7. Position 7 holds the letter S, so we append S. In the next cycle, the downward position is 2 times 4 plus 1, which is 9. Position 9 holds the letter I, so we append I. The diagonal position is 9 plus 2, which is 11. Position 11 holds the letter I, so we append another I. In the next cycle, the downward position is 3 times 4 plus 1, which is 13. Position 13 holds the letter G, so we append G. Now we check the diagonal character at this cycle. The diagonal position is 13 plus 2, which is 15. Since 15 is past the end of the string, this diagonal character does not exist, so we skip it and append nothing. In the next cycle, the downward position would be 4 times 4 plus 1, which is 17. Since 17 is past the end of the string, we stop the inner loop and finish row 1. The middle row has contributed the letters A, P, L, S, I, G. Now we move to the bottom row, row 2. Like the top row, the bottom row only receives characters on the downward stroke with no diagonal characters. In the first cycle of row 2, the downward position is 0 times 4 plus 2, which is 2. Position 2 holds the letter Y, so we append Y. In the next cycle, the downward position is 1 times 4 plus 2, which is 6. Position 6 holds the letter I, so we append I. In the next cycle, the downward position is 2 times 4 plus 2, which is 10. Position 10 holds the letter R, so we append R. In the next cycle, the downward position would be 3 times 4 plus 2, which is 14. Since 14 equals the length of the string, it is out of range, so we stop the inner loop and finish row 2. All 3 rows are now collected. We join the result list into a single string and hand it back. The final answer is spelled PAHNAPLSIIGYIR. Notice the structure. The top row gave us P, A, H, N. The middle row gave us A, P, L, S, I, G. The bottom row gave us Y, I, R. Reading them in row order produces the converted string. Every character was visited exactly once, and the cycle formula told us each position directly, with no grid ever built. Complexity. The running time is linear in the length of the string. We visit each character exactly once, so the total work scales with the number of characters. The extra space we use is also linear, since we store a list of the same size as the input, plus a handful of variables. Summary. Zigzag conversion comes down to spotting the repeating cycle. The ideas to remember are these. The cycle length is 2 times the number of rows, minus 2. Each row is harvested independently, cycle by cycle. The top and bottom rows take 1 character per cycle, and the middle rows take 2, 1 downward and 1 diagonal. Every position is checked against the string length before it is used. Thank you all, and see you next time.